everybody. Today, let me welcome you all for the session of Z transforms, which is a continuation of my first sessions. Now, this topic is coming under review for 4th semester students in module 5. Right? Now, in my previous sessions, we discussed Z transforms techniques and how it has been used to determine, to analyze discrete time sequence X of n, and signal systems better, and to design digital filters better in case of analyzing, right, any processing, any signals. Now here, and we have compared that Z transform with Laplace transforms, Fourier transforms, and we have solved some two simple problems. That is, right-sided sequence u of n, right, exists from 0 to infinity, and left-sided sequence only, that is minus infinity to 0, right, that is u of minus n. And we discussed, we have drawn reason of convergence, where exactly it converges, and in the Z domain we studied all these things. Now today we will discuss complex signals. That means in a signals X of n, if both right-sided sequence and left-sided sequence comes in one sequence, how exactly, right, how to find out Z transform then, and then how to draw reason of convergence for such sequences. And finally, one more concept is called zeros and poles detections. Let me discuss all the three for a input signal X of n, discrete time signal X of n, if it is having both sequences, right-sided sequence and left-sided sequence in one sequence. Let me solve this and let me do all the three. Z transform, reason of convergence, and zeros and poles locations. For example, before doing this, I want to say what is right-sided sequence and what is left-sided sequence. U of n and U of minus n. That we have done last class. See, for example, this is right-sided sequence. If a sequence, simple sequence like discrete time sequence X of n is equal to 1 by 2 to the power n into U of n, right-sided sequence, then reason of convergence in Z plane exists after Z is equal to greater than 1 by 2. That means after 1 by 2 onwards, your reason of convergence exists. This is for right-sided sequence. And the left-sided sequence similarly, if the sequence is U of minus n, then reason of convergence comes inside 1 by 2. This is discussed in the last sessions. Now let me include both the sessions in one, both right-sided and left-sided in one, and let me plot RO, see how it looks. Then we'll analyze the signals. Right, that's what I'm going to do now. Now, for that, simple, let me start a problem. Here then, as usual, write first line as the Z transform equations you write. Standard equation, X of Z for an input is Z transform equation. Summations varies from minus infinity to plus infinity, two-sided. X of n, your input, into Z power minus n. This is the standard equations for any sequences, discrete time sequences to X of Z. Now let me use this. Your X of n input is now two-sided sequence, mixture of right and left. Substitute this, X of Z is equal to summation n is equal to minus infinity plus infinity. What is X of n? X of n is your input. Write that input. Minus of U of, please see this, minus n minus 1. Plus, this is left-sided sequence, 0 to minus infinity. Actually, in fact, minus 1 to minus infinity. Plus, 1 by 2 to the power n into U of n, right-sided sequence. This is input into Z power n, minus n. Now, before going to solve this, let me see what is U of n and what is U of minus n. Actually, in that, he is not asking U of minus n, he is asking U of minus n minus 1. Mirror image minus 1. Starts from minus 1 samples, and its amplitude is also minus 1. Let me see all the 4 in here. Right, he is asking, this is what I want. For right-sided sequence, I want U of n, RSS. For left-sided sequence, he is giving this, but actually U of minus n is nothing but it is mirror image of U of n. This also is asking, and I want U of minus n minus 1 in that. Also in that I want this this amplitude as minus 1 actually. Now let me see all the four here. You know this. This is a simple step functions which is given by U of n is equal to 1, defined by unit step functions is defined by U of n is equal to 1 for n greater than or equal to 0. Greater than or equal to 0. It exists from 0 to infinity. Right? N less than 0, sorry, this is reverse. N less than 0, its value is 0. That means this side its value is 0. Now see, n at 0, its value is 1. See, U of 0 is 1. N at 1, its value is 1. N at 2, up to infinity, its value is 1. Otherwise, its value is 0. That is called right-sided sequence, which is discussed last class. Last sessions, you can open my lecture 1. You will get it, all that. Now, same, what he is asking? He is asking left-sided sequence. Then, same mirror image U of minus n, if you write, whatever exists from 0 to infinity, it exists from 0 to minus infinity. Now its amplitude, see, U of minus n is nothing but its value is 1, less than or equal to 0 this side. Right, reverse actually. Then at 0 it's 1, at minus 1 is 1, minus 2, like this up to infinity it goes to 1. But what is required? It is not U of minus n required, U of minus n minus 1. That means signal starts from index minus 1 I want. That's why I am writing next this as U of minus n minus 1 is, it's not starting at 0, it starts at minus 1. That's the meaning is U of minus n minus 1 value is 1 at minus 1 and minus 2, minus 3 and minus infinity. That means summations comes from minus infinity to minus 1 up to here. Right? But actually this is also not required in my problem. My problem, what he is asking is amplitude of minus 1. This is nothing but minus means minus 1, minus 1. Therefore, it is not, amplitude is not plus 1 actually is asking. He is asking minus 1. Therefore, this should be actually downwards. U of minus n minus 1 is nothing but its value is minus 1. See, it starts from minus 1. At minus 1 its value is minus 1. At minus 2 its value is minus 2. Like that up to infinity. Now, this is required in Z transformations. Summation starts from minus infinity to minus 1. That's the meaning. Now let me go for, now the problem, it's easy now. It's over with this background. It is, go for Z transform now. X of Z is equal to, first of left-sided sequence, LSS. From where to where it starts actually? It starts from n is equal to minus infinity to minus 1. Because minus infinity to minus 1, this is LSS, minus infinity to minus 1. That is why, see, n summations varies from minus infinity to minus 1. Amplitude is minus 1 because minus 1 is there. Amplitude is, see this, minus 1. This is. Therefore, minus 1, minus infinity to minus 1 into z power minus n. That is the formula. Half of the formula is this. I am substituting this. N is equal to minus infinity to minus 1 into z power minus 1, first term. Similarly, second term. Second term is again, since it is U of n is there here, therefore, since U of n is there, what I am going to do is, now see, summations n is equal to 0 to infinity. What is here? What is x of n? 1 by 2 to the power n into U of n. U of n is 1. This value is 1 into z power minus n. That is the formula. For example, this is the formula. 1 by 2 to the power n into 1 into z power minus n. This term I am writing separately. That's all. This is second term. Right? So, first summation you will get from minus infinity to minus 1. Second summation 0 to infinity. Now, I know this formula. Let me leave this first one. X of z is equal to, right now I don't want to discuss this. Now I know the formula of this actually. This is infinite sum formula. It starts from summation 0 to infinity. Right, I will write this as like this. N is equal to 0 to infinity. 1 by 2 into z power minus n all to the power n, same as this. I'll write like this. Now I use infinite sum formula for this. I know this, last class I have used. What is that infinite sum formula says? Summation n is equal to 0 to infinity, alpha to the power n. In place of alpha I am having 1 by 2 z power minus n. If this is like the equation, then the answer is 1 by 1 minus alpha. Now let me make use of this. Alpha place I am having 1 by 2 z inverse, that's all. Now let me write that. Then this equation becomes 1 by 1 minus, what is alpha? Alpha is this, 1 by 2 z inverse. This is what? RH, second term. Now let me come to the first term. First term what it says? X of z is equal to minus 1 summations n is equal to minus infinity to minus 1 z power minus n is there. One formula is there actually. What it says, that formula, any summations, it starts from minus infinity to minus 1 this side. Minus infinity to minus 1 if it is. In the right side, z power minus n is equal to, right side it is same as 1 to infinity, same reverse way. This side, 1 to infinity. Wherever minus is there now, that is plus, z power plus. This is the formula. Now let me use this formula here. Minus 1 into summation n is equal to minus infinity to minus 1 becomes 1 to infinity. Z power minus n becomes z power plus n. That's all. I am making use of this formula. This formula here. Right. Now plus second term is same. 1 by 1 minus 1 by 2 z inverse. Now I hope I am clear. I am writing this by using this formula. Second term no problem. First term I am converting minus infinity to minus 1 as 1 to infinity instead of minus plus by using this. Next is, then you will get z transform ROC. X of z is equal to, now see this, one more formula is there, 1 to infinity, z power n is there now. This is nothing but one more formula is there. Infinite sum formula is there for this. What is that formula says? That formula says that infinite sum formula. Starting from 1, if it starts from 1, starts from 0 already defined. Summations n is equal to 0 to infinity alpha to the power n if is there, 1 by 1 minus alpha already used. But here summation starts from 1, it's not 0. Then alpha to the power n, if it starts from 1, formula is this. Alpha to the power 1 instead of this 1 by 1 minus alpha. This is the formula. This formula I will make use of it. Suppose infinite sum formula starts from 2 if it is there, what is the answer? Summations n is equal to 2 to infinity alpha to the power 2 if it is there, then answer is alpha square. That means if 2 is there, it's 2 by 1 minus alpha. If 3 is there, alpha cube by 1 minus alpha. In this case, 1 to infinity is there, let me use alpha by 1 minus alpha. In this case, instead of alpha, I am having z. Instead of alpha, here I am having z. This is not alpha. Instead of alpha, z I am having. Therefore, z by 1 minus z. That's why I am writing this as minus 1 z by 1 minus z plus 1 by 1 minus 1 by 2 z inverse. Very, very important equations of x of z this is. Right. Here, call this as equation number 1. Using these equations, we can find out reason of convergence. Where exactly it converges, we can write. Then apply conditions. Apply conditions. For example, x of, apply reason of convergence to get, apply this condition. X of z exists only if both the terms, this term and this term, both the terms satisfies the conditions. Then only we get x of z. Then what is the conditions actually? Condition is, this is the condition. This value, right, second term is there, no here, this letter, only mod z is less than 1 in this first term and 1 by 2 z inverse less than 1. Then only this x of z exists. Let me check what happens if z, mod z is equal to 1, then it will not exist. See this. For example, if mod z is equal to 1, what will happen? 1 minus 1 is 0, z by 0 is infinity, then you will get infinite terms. You will get unstable output of x of z. X of z has unstable output. That means, x, right? You will not get what is a stable state. That's why first term to get, right, x of z, you need to be, this should be less than 1. For example, mod z is less than 1 means, let's say z is equal to some 0.8. 1 minus 0.8 is 0.2. Then 1 by 0.2 is maybe 5z. Right? Then finite value will get. Similarly, second sentence also, second term also, 1 by 2 z inverse mod should be less than 1 here also. It should not be 1. 1 minus 1, 0. Again infinity. Infinity is not, x of z will not exist. Therefore, 1 by 2 mod z inverse should be less than 1. Therefore, that is nothing but 1 by 2 is less than mod z. That is nothing but mod z should be greater than 1 by 2. Second case, for the second term, mod z should be greater than 1 by 2. For the first case, mod z should be less than 1. Then you will get region of convergence as it should be greater than 1 by 2 and less than 1. Right? That means its value mod z, if it is greater than 1 by 2 and less than 1, then only region of convergence you will get. X of z gets z transform exists. Now let me plot by using this region of convergence. Let me plot it in z plane. For example, in a z plane, real z, imaginary z, let us say this is z plane, right? Here, what is the condition? Mod z should be greater than 1 by 2, less than 1, like we discussed. Then you will get, see, this is 1 by 2 distance, this is 1 distance. Draw the circle. Now region of convergence is coming between these two, see, between these two rings. It should be greater than 1 by 2, should be less than 1. That means these are the reasons, these regions are there, no? Center of the ring, that is called, center ring is called region of convergence. This is how Z transformations is used, right? To analyze any signal, any complex signals. For example, simple signals also we see. Here if it is, if signal is having both right-sided and left-sided sequence, then region of convergence in the Z plane we get like this only. In between 1 by 2 and 1. Right? Now, this is second concept. Then my last step is zeros and poles. I said now, zeros and poles locations. Here, just see this last part of this session is zeros and poles locations we have to plot here in this Z domain. Right? For that concept, what is just right now in this diagram, observe this. For example, two zeros. Zeros are represented by zeros only. See this at 0, 1, 0, and on the axis at 3 by 4, one more 0 I have written. On this Z plane axis, I am having two zeros represented by zeros only. 1 0 at 0, other 0 at 3 by 4. Time being, we just see this. Later we'll solve and we'll find out how we get that. Then two poles. Poles are indicated by stars. Zeros are indicated by zeros. Two poles exist. That is indicated at 1 by 2 and at 1. Right? Two poles are there and two zeros are there. Now how to get these two poles and two zeros on the axis? We will see now through the equations. Now let me continue. Whatever the first equations we got now, let me continue that equations. For example, we stopped here. Right? This equations we stopped somewhere here. Equation number 1. Right? We have done this and here we have stopped now. Let me extend this equation. Let me go for simplifications of these equations and we will get one more equations. Ratio of x of z as ratio of simplifications of 1 and get 2. That is ratio of numerator by denominator. Z polynomials actually. Then by using that equations we can see those zeros and poles. Right? Now for example, let me do the continuations of that equations 1. Equations 1 continuations is this. X of z is equal to, what is there in the denominator? 1 minus z. 1 minus 1 by 2 z inverse is there. 1 minus, see this. See these equations. For example, see these equations. Take out 1 minus z. 1 minus 1 by 2 z inverse. It's a maths actually. This one, right? 1 factors and this one factor, and then 1 minus z into 1 minus 1 by 2 z inverse in the denominator. Then z into this plus 1 into this. That's what I am doing. For example, see. Minus z into 1 minus 1 by 2 z inverse plus 1 into 1 minus z. The denominator is same. Now maths, denominator is same. Now simplify numerator. Minus z, minus into minus plus, z into 1 by 2 z inverse is 1 by 2 plus 1 minus z is equal to minus 2z plus 3 by 2. This is, see, 1z minus 1z minus 2z. This is plus 1 by 2 is plus 3 by 2. Denominator is same. Denominator is same. Right? Now, immediately take out this minus sign outside and cancel it. For example, maths I am doing. Minus 2 of 2z. Minus into minus is plus. Minus into minus is plus. Minus 3 by 2. Then here, take out minus from this. Minus of z minus 1. This is same as this. Right? Then second term 1 minus 1 by 2 z inverse. Then answer is 2z minus 3 by 2. This minus minus gets cancelled. Right? Now 2z minus 3 by 2. By denominator is z minus 1. 1 minus 1 by 2 z inverse. Now see this denominator, last step. Whatever note down the power of z minus z inverse. Whatever the power of z inverse is there, that much multiply and divide by z. You have to do. Suppose here z minus 1, z power minus is 1 is there, then multiply and divide by z. If it is z power minus 2 is there, multiply and divide both numerator and denominator by z square. That's all. If minus 3 is there, z cube. Only simplification's purpose. Then see that z into z both sides here is there, numerator denominator. 2z minus 3 by 2, z minus 1, 1 minus 1 by 2, z inverse. Now this z into numerator becomes 2z minus 3 by 2. Numerator is this. Numerator is this. Right? Denominator is z minus 1 you write as it is. This z you bring it inside. Because to locate poles and zeros, I want z minus 1, z minus 2, z minus 3 like. That's why I am doing this z inside. I am bringing this z inside. This becomes z minus z into 1 by 2 z inverse is 1 by 2. Then you will get these equations. Very, very important equation this is. Using these equations 2, we have done zeros and poles. Always you will get equation 1, then plot arrows. Then try to simplify it, you will get ratio of numerator and denominator polynomial. Now, for example, see, numerator in these equations gives poles. Numerator in these equations gives poles, right? For example, numerator gives zeros, denominator gives poles. Now, for example, goes to numerator. What are the terms of z is equal to 0 is there? Therefore, first 0 you will get at 0 only. That's why z1. At 0 you get 1 0 if you remember. Then second term you see 2z minus 3 by 2 is there. 2z minus 3 by 2 is equal to 0. Solve this. Z is equal to 3 by 4. Therefore second 0 you will get at z2. That's why 2 zeros you are getting, see, at z at 0 is equal to 1 0, that is z1. At 3 by 2 4 you will get second 0, that is z2. Zeros, 2 zeros are indicated by z1 and z2. Similarly, poles. 2 poles are there. 2 poles, right? Now poles are, again say, denominator comes z minus 1 is equal to 0. Therefore z is equal to 1. You will get first pole at P1. Z is equal to 1, you will get first pole and it is indicated by star. Then similarly z minus 1 by 2 is equal to 0. Solve this, z is equal to 1 by 2. Then you will get second pole at 1 by 2. P2 second pole indicated by star at 1 by 2 you will get. That means one pole at 1, other pole at 1 by 2. That is shown here. Right, see, at 1 by 2, one pole indicated by P1. At 1 you will get second pole indicated by P2. This way you will get totally 2 zeros and 2 poles. Zeros are indicated by zeros at 0 1 0, at 3 by 4 1 0. Then poles indicated by stars indicated by P1 P2 and exist at 1 by 2 and at 1. This way we can use the transform, right, to determine poles and zeros, and we can analyze your discrete time signals x of n better compared to any other transforms here, and which by doing that means what we are doing here, let it give any complex input signals x of n discrete time signals. We can find out z transform and we can plot region of convergence in z plane like this, and that comes a ring actually here, right, that is greater than 1 by 2 and less than 1, and plots, we can plot poles and zeros, right, and here in this particular complex signals we are having 2 zeros and 2 poles, and zeros are indicated by zeros, poles are indicated by poles. This way, this gives flexible analysis actually to any input signals, which is very important in processing today's complex processings like image or video or audio, whatever it may be. And that's why this topic is really Z transform is really helpful to design any project, real-time projects. I hope I'm clear. Next class, let's see more on properties, Z transform properties, right? Where we'll deal on properties of Z transform, which gives more flexibility to design or analyze discrete time signals X of n. I hope, yeah, that's all it seems. Thank you.